Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. We spent the last two videos writing a compute shader for light culling and now we are ready to use it. So today we are going to set up the buffers and data structures that are needed in order to run this shader. First, we want to extend the root signature with new root parameters for light culling. We already added the enumeration for the global index counter, and we can continue with frustum buffer as input, light culling info buffer, and light grid and light index list buffers for opaque objects. Here we have a data structure that we use to hold everything related to light culling per render surface. We can add the new light culling buffers here. We use a single D3D12 buffer for both light grid and light index list buffers. I'll skip light index counter for now, since it's handled a bit differently for reasons I'm going to discuss later in this video. Next, we need to have a variable that contains the dispatch parameters for the light culling shader. Because we are sharing a single resource for the light grid and light index list buffers, we keep the address of light index list within that resource. Note that these buffers are accessed only by the GPU and therefore there won't be a trivial way of clearing them when there are no lights in the scene. We could keep running the light culling shader, but that wastes performance for scenes that have no callable lights, such as outdoor scenes with the sun as the only directional light. So what we do in this case is that we run the shader just once, which will effectively set the light count per tile to 0 in the light grid. Then we can skip light culling for as long as there are no callable lights in the scene. That's why we have this variable that is initialized to true in order to run the shader at least once. The light culling root signature can be used for both grid frustum shader and the light culling shader. However, we do need to create a pipeline state object for light culling. Now we can define the additional root parameters when we create the root signature. Grid frustums and light culling info buffers will be accessible as shader resources, and are therefore attached as shader resource views. The light grid and light index list buffers will be written to by the light culling shader, hence they are attached as unordered access views. As always, make sure that the register numbers are the same as the ones we use in the shader. We create the pipeline state object for light culling next. This is similar to the code we have here, except we use a different shader. The function returns true if both PSOs were created successfully. And we release the PSO when the renderer is shutting down. We need to modify the code in resize buffers function in order to create the additional buffers for light culling. First, we calculate the buffer sizes. These sizes are aligned up to 16 bytes because we are putting multiple buffers in the same resource. Each tile in the light grid buffer contains 2 unsigned integers and we have as many tiles as we have frustums. The light index list buffer is just an array of integers. However, we need to define how many lights we expect on average to affect each tile. I'll define 256 lights per tile, which is way too much, but it doesn't hurt to have a bigger buffer either. So the buffer size is 4 bytes times max lights per tile times the number of frustums. Note that 256 is the average per tile. So some tiles could have 0 lights and others up to 1024 lights, which is the maximum array size in our light culling shader. Now we add up the buffer sizes in order to get the size for the resource that will contain both buffers. In case this size is larger than the current buffer, we'll create a new buffer. Oops, I made a typo here. Not sure why I wrote this in reverse, but we create our D3D12 buffer first using the total buffer size and assign it, which will release the old buffer if there was any. Note again that this resource is not CPU accessible. Then we get the start address of the buffer and add the light grid buffer size to get the address of the light index list buffer. We fill in the dispatch parameters next. As I explained before, for light culling shader, each thread group is a tile and the number of threads in X and Y directions is simply the screen width and height aligned up to tile size. Now, I kinda need to make a little detour here and write a new buffer class type, which I call a structured buffer, for lack of a better name. And we'll be using it for the light index counter. Obviously, we have been using buffer resources as structured buffers in our shaders already. However, those buffers can't be cleared on the C++ side when they are not CPU accessible. And in case of light index counter, we do want to be able to reset the counter after each frame by setting its value to 0. I'll explain how this works as we write this new class. It has a D3D12 buffer type as its internal buffer, and because it's a structured buffer, we use a stride, which is the same as the element size. We have two additional data members. These are descriptor handles for unordered access views of the same buffer resource. However, one of them is in the shader visible descriptor heap, and the other is in a non-shader visible descriptor heap. I'll write the move related functions first, just to get those out of the way. This class is not copyable, so the only functions that we need to write are the move constructor and the move assignment operator, which in turn call move and reset functions here. Of course, we also need the structure and release functions. Now we can use a command list API function in order to clear this buffer with some value. And there are actually two of them. One for clearing the buffer with integer values, and another one for clearing the buffer with floating point values. So for integers, we call clear unordered access view uint, and for floats, we call clear unordered access view float. Next, I'll add the usual accessor functions to get the GPU address, buffer size, and the UAV descriptor handles. Finally, we add a static function that returns a default buffer init.info struct for this buffer type. Note that we have allow unordered access flags set by default. The only functions left to implement are the constructor and release. Starting with the constructor, we create the internal buffer and assert that the size is a multiple of stride and that the alignment is non-zero. We can use this class in the same way as a D3D12 buffer. However, we can choose to create unordered access views for it if we want to be able to clear the buffer in the host application. In that case, we allocate space for the descriptors. One of them is allocated on the global UAV descriptor heap, which is not shader visible. The other one is allocated on the global SRV heap, which is shader visible. Then we proceed to create a UAV for the internal buffer resource. This is the non-shader visible UAV. We can then copy this UAV to a shader visible descriptor heap using copy descriptor simple function. In the release function, we free the allocated descriptors and release the internal buffer. So now the light index counter can be a structured buffer. We only need to create it once because it always has the same size. Before we are able to dispatch the light-culling compute shader, we need to be able to get the callable light count, callable light buffer, and culling info buffer. We can add a few functions that are similar to the ones for directional lights. Now we can fill in the dispatch parameters. Number of threads and thread groups are already in here, so we only have to set the number of lights and the depth buffer SRV index. At this point, if the number of lights is 0 and lights has been set to false, then we know that we don't have anything to do and we can return. However, if there are callable lights in the scene or has lights but still true, we run the light-culling shader. First, we copy the dispatch parameters to the global constant buffer. Then we transition the light grid and light index list buffers to writable state. Because we are going to run the shader next, we need to apply this barrier immediately. We also need to clear the light index counter. In the same fashion as we did other dispatch and draw function calls, we set the root signature, pipeline state object, and the root parameters. Note that we use the same slot to set the light index counter for light-culling shader. This slot was used for frustum's buffer in grid frustum shader. It's in general a good idea to keep the root signature as small as possible. At the end, we dispatch the thread groups and transition the buffers back to readable for the pixel shader. When we try to run the application, we get an error from the debug layer that says that we can't use the UAV clear functions with structured buffers. This means that a structured buffer was probably not the best choice for what we are trying to do. In the next episode, we are going to try and do it correctly. But for now, we can suppress this error since it's generated by the debug layer. To suppress this error, we can add a filter to the debug layer when we initialize it in core.cpp. Here we see that there is a message ID just for this error, which we can put in an array and pass it to the info queue, like so. Great, we can run the application now. However, when I close a window, it triggers an assertion failure. So I must have made a mistake somewhere. Let me inspect the data for a bit and see if I can find it. I see I forgot to call reset after the stuff in structured buffer is moved, so it's copying instead of moving the data. Calling reset should fix the issue. Nice, it seems to be running fine and we don't have any live objects or memory leaks. So in the unlikely case that I haven't made a single mistake in our shader code, we might be actually calling lights right now when we run engine test. We just can't see it because obviously we are not using the lights yet. So in the next video we are going to try and add visualization for the light-culling shader and also implement simple lighting using our point lights and spotlights. As always, thank you for joining me today and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering.